do it. Okay, so Fabio, it is your show. You're welcome to share the screen and start your.
Thank you.
And
yes,
to the participants, this is in the Zoom seminar style, so each of you has the right to ask questions at any time. If you have urgent questions, I'm sure that Fabio will be happy to answer them in between. If not, we can have a question and answer session after the talk. So Fabio, please, we are very interested to see what you're going to tell us today.
Thank you so much. Thank you so much for the kind words. And actually, thank you for the invitation. It's a pleasure. And yes, as Francesco was saying, please interrupt me. This is, I would very much love for this to be an interactive discussion. So just stop me at any time. There's no problem. And we can talk about any questions you might have. All right. So this is the title, Kinetic Theory of Information Transport. Let me tell you a little bit about what this is about. First, I'm going to put this, oh, sorry. I'm going to put this, this link in the chat so that you can, sorry, wrong. There you go. Let me put it in the Zoom chat. So you can load it, and it takes a bit, but I'll show it in a moment. All right, so what I'm going to talk about today is a set of, essentially a part of a set of works that I started a year and a half ago on using essentially differential geometric techniques to study the physics of quantum systems. And this is broadly intended as, you know, quantum information flows, the dynamics of quantum systems, and a bunch of other tools that maybe I'll have some time to talk about. But today in particular, I'm going to discuss this work, a kinetic theory of quantum information transport. So this is kind of focused a little bit on that. I want to tell you that we have also a geometric quantum mechanics exploratory seminar series. So if you're interested in the topic, send me an email and you're welcome to attend. All right. So what is the, you know, scientifically and physically, what is the long-term goal here? And if I have to summarize it in one sentence, is to be able to describe, to have a full-fledged theory to describe how many body quantum systems that interact with highly structured environments are able to process information. So if I have to compress it even more in one sentence, is how they're actually able to compute. And so today in particular, I'm going to answer a subset of questions, which goes into the direction of trying to better understand how, if I have the quantum states, the state space of a quantum system, how does probability flows around that state space as a result of its interaction between the system and the environment. And the result of trying to come up with a theory for that is this kinetic theory of information transport. So the theory has three crucial ingredients. First is geometric quantum mechanics. Then, of course, there is the use of geometric quantum mechanics for open quantum systems, and in particular to describe their dynamics. And then there is a kinetic theory approach on top of that. And the result of mushing these three things together is this kinetic theory of information transport. All right, let me start with geometric quantum mechanics. So the examples that I'm going to go through are for qubits, just because it's easier to visualize. But the theory is completely general in the sense that it's exactly as I'm presenting it for any. Yeah. You have a question? Oh,
no, probably someone that is not muted. I will mute everybody.
Oh, I see. Okay. Okay.
Sorry for that.
No worries. So the theory is exactly as I'm going to present it for any finite dimensional quantum system. but it is possible to use it for infinite dimensional quantum systems. So like, the usual particle in a box or anything that has continuous variables. But I'm gonna focus on finite dimensional quantum systems. So the standard approach to quantum mechanics has three key objects in the theory, right? There are states, which are vectors in a Hilbert space, complex Hilbert space. Observables are self-adjoint operators or matrices, because this is finite dimensional. And the most fundamental dynamical description that we have is Schrödinger's equation. And then when we embed this into a larger system and we look at a part of it, the dynamic is an open quantum system dynamic. Now, the theory has what I call two descriptive redundancies. And what I mean by that is that we know that, states, vectors that differ for an overall normalization or an overall phase, they're different mathematical vectors, but they're the same physical state. And a very similar situation happens for within the density matrix formalism. And we know that any density matrix has, in principle, an infinite number of decompositions that gives you the same density matrix. And so these are, in some sense, descriptive redundancies, in the sense that we have some, some additional mathematical objects that we might want to get rid of or pinpoint. So the right question to ask, if one wants to understand, want to kind of come up with a theory to understand how probability flows in the state space, is to first start asking, what is the geometry of the state space of quantum systems? And this is a question that, this is not my work, so I'm just presenting the theory that, just for historical, a couple of historical notes. The theory was, the way, at least the way I learned about it, is that essentially there was some work. The first one that looked at it was Strocchi, is an Italian physicist, and now he's retired, who noticed that there were analogies between a classical description, essentially, of quantum mechanics. And then it was kind of rediscovered repeatedly. A lot of work that I know about this was done by Brodie and Houston. They are two mathematicians in the UK. But then there is really, really a lot of people, and I just don't want to pick names, and it's, it has been rediscovered over the years. So I'm just going to tell you the quick story. So the way this goes is that you have a generic Hilbert space, right? And you fix a basis. This could be, interferometric measurements, for example, and you parameterize the vector space, the psi of z, with a bunch of complex numbers, right? Z, k. Now, the point is that, of course, we can arbitrarily fix normalization. We can fix it to 1, so we interpret it with probabilities, or we can fix it to the number of sampling, the number of samples. So we essentially, we're looking at it as countings. But we are also allowed to rescale the vectors by an overall equal phase. And so in just one equation, essentially, this bunch of vectors, if you multiply all of them by complex numbers, so a real part and a modulus and the phase, then you get a different vector, but the same physical state. And so one would like to get rid of this. And mathematicians have studied this, this space, and it's called the complex projective space. Has a very nice geometric structure. For the people who are more kind of versed in this is a Kähler space. It means it has two notions of geometry. One is Riemannian, which is the standard notion that we use to compute length, areas, volumes. But it also has a notion of symplectic geometry, which is the geometry that describes Hamiltonian flows in classical state space. So what does this mean for the three crucial objects, states, observables, and dynamics for geometric quantum mechanics? And I'm just going to quickly go through and compare the two in the standard and in the geometric formulas, just to give you a more accurate idea of what this means practically. Well, okay, states are pure states are vectors in a Hilbert space, or in geometric quantum mechanics, we can actually think of them as points on a manifold. And the most well-known example of that is the block sphere, obviously, which is the quantum state space of a qubit. It's a two-level system, and you choose two angles, theta and phi. And so you can easily parameterize Z with two angles, theta and phi. And essentially, cosine of theta over 2 and sine of theta over 2 e to the I phi, they are the elements of Z. But you can change coordinates, and the change of coordinate can be, for example, highly nonlinear. Like, for example, this change of coordinate, we're going from theta phi to p phi, where p is the probability of finding the system in the eigenstate 1. And this is a slightly different representation, but it's the same mathematically and geometrically. They're the same object. They completely describe the state space of a quantum system. And have this in mind, this decomposition probability phase, because everything that I'm going to say is kind of, it's easy, it can be understood in an easier way if one thinks about probability and phases coordinates. And so it's also arbitrary. In this case, we just have p and phi, but in arbitrary dimensional systems, you have p n, phi n, but the situation is exactly the same. All right, so we're dealing with points in a manifolds. What are observables? Well, this is actually quite easy. You take the matrix or the operator. And so as we said before, states are points on a manifold. So basically we have parameterized the vector and Hilbert space with a point on a manifold. Now, of course, the expectation value of this operator on that point is a function of the point. And it's a well-defined function. Basically it's a quadratic function. The contraction is done with complex values, but because the operator is self-adjoint, then the FO of Z is always real. And so this is how you map observables in Dirac's quantum mechanics with linear algebra into observables in geometric quantum mechanics. They're just quadratic functions. And this is an example of how they look like for a qubit. All right, and so again, in the qubit, these are three examples where the square is just the block square, with p and phi coordinates. And here I'm just depicting the three fundamental observables, which are the expectation value of the three Pauli matrices, sigma x, y, and z. And this is color coded, so the value of the observable, it's in the color. The darker, the higher; the lighter, the lower. All right. Then dynamics, and here comes the kick or list. That's where it came for me. You take your Schrödinger's equation, and you take the Hamiltonian operator H, and you do the mapping from Dirac's quantum mechanics to geometric quantum mechanics. So you compute the observable associated with the Hamiltonian epsilon of p phi, and this gives you a function of p and phi, and you can prove that without any classical limit, there is no h bar going to zero limit here. You can prove that Schrödinger's equation is exactly equivalent to Hamilton's equation of motion. And this is the form for the qubit, where p and phi are those coordinates on the block square. But the result is absolutely general for arbitrary finite dimensional quantum systems and also infinite dimensional ones. That basically Schrödinger's equation, so the unitary flows, are described by Hamilton's equation of motion on geometric quantum mechanics. So there is this duality between unitary flows, Schrödinger's equation, and actual Hamiltonian classical mechanics. And again, for the more geometrically minded people, this is because the complex projective space, it's a color space. So basically you can define a notion of Poisson brackets. And so once you have that, basically you can define classical flows, Hamiltonian flows. All right. Second part. So this is kind of the mathematical apparatus. What do we do with it? We want to tackle the physics of open quantum systems. So naively, the first thing that we ask is, how do we handle uncertainty? So right, when one tries to go from pure states to mixed state, one of the naive thing to think is what happens, like pure state corresponds to a certain knowledge of the system. What if I don't know exactly what the state of the system is and I have a certain probability distribution? Well, okay, then let's use probability distributions on the state space of a quantum system, or more accurately, probability measure. And in order for us to derive a probability measure for an open quantum system, the question that needs to be answered is, and this is not just a technical question, this is also part of the philosophy behind the work. And so the question is, how does the detailed structure of correlations between system and environment basically determines the state of the system? And the philosophical part behind it is that if you think about, I don't know how many people are familiar with this, but with the charge of larger Hilbert spaces approach, that means that basically, if I have a system that does not evolve unitarily, I can always enlarge my description, include the environment, and then get a description that is basically that follows Schrödinger's equation. So the idea here is that the detailed structure of the globally pure state obviously completely determined the evolution of my open quantum system. And so in some sense, in some detailed and specific sense, the detailed structure of the correlations between the information theoretic correlations between the system and the environment are the ones that determine why and in what way the state of the system comes to be because of those interactions. So it's basically thinking about the state of an open quantum system as resulting entirely from the structure of correlations with its environment. So in order to answer the question, you begin with the usual setup. You have, this is the system we're interested in, system understudied sometimes. You add an environment, and you fix two bases for your system and your environment, and you write your globally pure state as a general state. Now you can prove that you can always write these psi in the following way, as essentially as a sum over one index. Now, people that are familiar with the Schmidt decomposition will recognize something similar. This is not the Schmidt decomposition. In some sense, this is the exact opposite of the Schmidt decomposition, because the Schmidt decomposition runs over the labels of the system. So it's kind of a minimal number of states in this decomposition, while here the index runs over the dimension of the environment. And now the advantage, or this is what this gives you. Well, this X alpha are just the probability that if I make a measurement on the environment, on the eigenstate E alpha, I get some eigenstate E alpha with probability X alpha, and the Y alphas are essentially the possible post-measurement states. So you make a measurement on the system and you look at what the state of the, you make a measurement on the environment on E alpha, you look at what possible state the system can be in, and you find that given that you get alpha, E alpha, then the state of the system will be Y alpha. And so you can directly compute the density matrix is, you can do the partial trace, and you realize that in this basis essentially gives you like a diagonal decomposition. It's not diagonal in the strict sense, because this sum goes from one to the dimension of the environment. And so the states Y alphas are not, they're not orthogonal to each other. They don't form a basis. They're actually, there is a lot of them. But the advantage is that this does uniquely define a measure on the space, on the state space of my system. And the measure is essentially the ensemble on the system that is determined by the environment. And the idea here is that, again, the ensemble contains and conveys the information about how the structure of relations between system and environment basically determine the state of the system.
I have a question, if that's okay. So I'm a bit lost here, because like normally when you when you were explaining the previous slide, in my mind what I was doing is like you take a density operator and then you like obtain its purification. So what I would do is I would sort of diagonalize the density operator and then afterwards, get the Schmidt decomposition. But like, so over here, if these Y alphas are, so I mean, how do you obtain the purification to begin with? Like if you're not using, like what environment, so how does the environment come in? Like my notion of like purification is like, you do the diagonalization, then you get a purification. But over here, the purification starts with the environment, or it comes with the environment. So how do you do the purification in that place? Or is
this is not what I'm discussing here is that your starting point are both system and environment, right? So my point here is that, and I mean, this is not obvious at this stage, but essentially the purifications at fixed environment size. So say that you fix you're saying, my environment has dimension, whatever, 100 qubits, for example.
Right.
Those purifications are essentially in one-to-one correspondence with measures on the state space. So basically, as you can see here, I mean, this is, I'm not giving you right at this stage a mathematical proof. I have one, but it takes a bit to go through it.
Sure,
intuitively. But intuitively, the reason why this happens is the following. If you look at psi,
right,
I proved, and this is published, so that you can always write it like this, okay? Now, intuitively, if you vary like this E alpha, it's a basis of your choosing. You choose one, it doesn't, it's one, you have chosen it, whatever.
Yeah,
there's no particular role. But because of that, if you vary X alpha and Y alpha, you can essentially change psi and cover the whole set of states, basically, of pure states in the global Hilbert space. So this is essentially what it's essentially reversing that perspective and saying, I want to be able to talk about purifications and ensembles so that they are different, but they give me the same density matrix. Okay.
Okay. So the point that
they don't always have to give me the same density matrix.
So that the point that they can, like, you varying X alpha and so Y alpha, so varying X alpha and Y alpha, and using that you can cover the entire set of pure states. That doesn't seem obvious to me at all, but I guess like there's a proof for that, right?
I agree. It's not obvious at all. The proof takes a little bit of time, but we can talk about it later. It's essentially what you do is that I mean, it's a geometric proof. So you have this ensemble, and you can define a notion of distance. And so basically you prove that given that there is a one-to-one correspondence. So given that X alpha and Y alpha are always close to some X tilde alpha and Y tilde alpha, then the psi globally is very close in Fubini's 2D metric with the psi tilde, and also the converse is true.
So there would be a minimum size of the dimension of the environment for this to work, right? I mean, it wouldn't work for dimension D's. I mean, environment is just one dimensional. It wouldn't work for that, right? Or would it work for any dimension of the environment?
It would work with any dimension of the environment, but you would be covering different spaces, right? Here, the label is on the environment. So say that I have, if my environment is made by 1 qubit,
right?
So I have 2 qubits, then this decomposition covers the space of 2 qubits.
Right.
If the environment is larger, then you are able to cover larger, globally pure states.
Okay.
Right,
okay.
because I mean, the trick is in here. Like this is, I mean, it's not a problem. The Schmidt decomposition, that we do it so that it doesn't scale, right? But this does scale with the size of the environment. So the larger you take this measure,
okay,
essentially you're effectively considering environments of progressively increasing size.
okay. Thanks.
Is that, yeah?
Yeah, I mean, I have to think about the later part, but yeah, and thanks for the explanation.
For sure. And please keep asking if something is not, you know, doesn't feel right. I'm more than happy to talk about it. All right. So yes, the suggestion here, the idea is to look at probability distribution on the space of pure states, to do the physics, model the physics of the ensemble behind the density matrix, because it's essentially describing the evolution is in a larger pure state, in a larger space where the whole thing is in a pure state. Now, this is the way you do the basically ensemble, right? It's telling you that with probability X alpha, the system is in a state described by the ket Y alpha, and you can say this by putting a probability measure on the space, on the complex projective space, and this is obviously the probability measure. It's a convex sum of Dirac deltas, where here, you know, the Y alpha here is the vector in complex projective space, and Z is just the coordinate spanning the full space. Time evolution, obviously, as we discussed a bit before, when your global pure state evolves, you're essentially changing X alpha and Y alpha, and these things basically change the full probability distribution that you're putting on the space on the state space of your system. And so here comes this is why I've put the, yes. Can you see my screen, and can you see the sphere?
Yes, we can. Thank you.
All right. So this is an example, a dynamical example of using this technique to see how the ensemble changes. And in this example, this is it's an XXZ spin chain. It's a set of 11 qubits that interact with a Hamiltonian that is an XXZ Hamiltonian, and I'm looking at the at one qubit as my open quantum system, that it's kind of in the middle of this 11 spin chain. And the simulation, the whole thing starts in a pure state, sorry, in a tensor product state, so that when you do partial traces, you still get a pure state. And then it evolves. The whole thing evolves unitarily. So my system evolves in a open quantum systems way. It's in a non-unitary way. So at t equals 0, you can see that there's only one point, and it's concentrated in the North Pole. And this is because the global pure state, it's a tensor product. And so the reduced state is just pure state. So there's only one point. But if I let it evolve, this is what you see. So this is a short time evolution that I've prepared here. And so what these things are, just to give you an idea, the point, the location of the point is the Y alpha. The color of the point is the probability mass that it's carrying with it. So it's the X alpha. And so you can tell that basically what you have is that the system starts in a configuration in which there's only one possible state the system can be in, and then it splits off. It trifurcates. And if you're wondering, like, you can tell that basically what happens is that the point progresses in the initial direction, and then two more split off. And you can see that this happens in a kind of a fractal way, in the sense that each of these clusters trifurcate and then trifurcates and then trifurcates until it's essentially covering the full sphere. And the reason, if you're wondering why the number 3, it's not dark magic or whatever, the number 3 is essentially the XXZ chain. It's a nearest neighbor Hamiltonian, means that each qubit interacts directly with the one on the left and the one on the right. So there are 2 qubits with which my qubit interacts directly, and this is true for every qubit because this is closed boundary conditions. And so basically the number of new clusters that are formed are equal to the number of qubits my qubit interacts directly with. So for example, if you do the same thing in a 2D Heisenberg chain, you see instead of going in 3, it goes in 5. Or the same thing happens if instead of putting the XXZ, the nearest neighbor model, I add next to nearest neighbor interaction, you still see the same kind of behavior. All right. So this is just to give you, a mental picture of what's happening, let's try and build the kinetic theory of those, because it's very appealing that you can think about these points as particles moving on a quantum state space. So this is our mathematical object. We have a measure on the state space of a quantum system, and it evolves as a function of time, and it's essentially a bunch of points, or as a measure, it's a convex sum of Dirac deltas. Now, what you can do is that, this is how you build the theory. You take your this object, I call it a geometric quantum state. It's a time-dependent measure on the space of a quantum system. You do the time derivative, and you recognize that there are basically 2 different contributions here. One that comes from the fact that the probability mass themselves, they depend on time. And the other one, which is this one, it's essentially due to the fact that those points, they move on the sphere. So they carry probability mass with them across the state space of a quantum system. And now the nice thing is, because of the form and basically because of the geometric structure, you can check that this geometric quantum state satisfies a full-fledged continuity equation for information transport, in the sense that these 2 contributions have have the standard physical intuition that we put on transport theories. And so let me address that. Let's start first with the flux. So, the usual form of the continuity equation is that time derivative equal the divergence of the flux plus the source or sinks terms. And this is how we describe, hydrodynamics. This is how we describe linear transport of mass, of charge, of momentum, of whatever. My point is that we can do this to describe the linear transport of probability across the state space. And so it's the movement of information as a result of the interaction between system and environment. So what is this object J? Well, it's kind of, it has the standard setup. So if I identify a small region here, this is a cartoon of my projective Hilbert space, which is the quantum state space. At each time, you have a certain amount of particles that belong to that region. And as you have seen on the sphere, there's essentially a flow of these particles across that region. And this is the way you write, it's directly the way you write the flow. And you can, if you're interested in the flow in a particular region, you can use the usual, I think it's Stokes Theorem, and essentially check that this term basically is the integral of the flow across the boundary So it's telling you basically you're setting up equilibrium equations so that you're saying that stuff is not destroyed, right? If it's overall, if this quantity overall is fixed, but not locally, then you cannot destroy this quantity, but you have to move it across the state space. And this is exactly what's happening. And this is one way in which this can move. So think about the case, for example, in which x dot, so the probability mass as a function of time is fixed. And then this is the only term that is important in the continuity equation. And so there are particles that carry probability mass with them, that move with a certain speed across the state space. The second term is the sigma term, is the source term, and you can think about it in the following way. This is a genuinely non-local term in the state space of a quantum system. So imagine the converse of the previous situation. Imagine the situation in which each of the points that you saw on the sphere had a fixed position. So this doesn't, the shape doesn't change. Can I still have some non-trivial dynamics? The answer is yes, because each of those points carries a probability mass that depends on time. And so, for example, you can have situations in which two points that have a certain probability x alpha and x beta, and they're far away in the state space, they can still change. They can exchange a certain amount of probability epsilon, and this is allowed as long as the total amount of probability, which is 1, is conserved. So these are the two terms, and they follow exactly, you know, this is like a standard theory of transport. There is really nothing different aside the actual geometry of the space, which encodes the quantumness of the fact that we're describing a quantum system, not a classical one. So this is another, oh, why is it not, oh, here. So this is another example of a numerical simulation of this situation. Here you have basically, this is like a classical gas. In the top left corner, you see this is it's a classical gas of particles. But we imagine that internally these particles carry a spin, and essentially this is the evolution that I plotted here is like a mean field, where each particle, the spin of each particle evolves as a result of the magnetic field created by the spins around that particle. And of course, it depends on where, if two particles are close to each other or not. And you can see that the way it starts, it's very organized. This is the P phi coordinate. So what you're seeing here as 2 points that move, this is essentially on the block sphere. This is just, you know, a rotation generated by some Hamiltonian in a fixed direction, because that's how it starts. But as you progress in time, wait, too fast, you can see that basically the points start to divide and start to fill basically a slightly different flow. And I've plotted the flow, the information flux, in the bottom right corner. And basically those are the derivatives of the points at each time. And you can tell that there is basically some kind of pre-thermal state that survives for a little bit of time, because if you do the time average of the distribution up until kind of here, you basically stay on these two lines. But after a while, you can see the onset of basically fully chaotic behavior. And I'm not going to keep watching this, because this is just, I mean, it stays this kind of chaotic behavior. All right. So how do we use this to describe actual concrete systems? Let me check the time. All right. The first thing that we want to describe is isolated system, because kind of warm up for open quantum systems. Isolated quantum systems have no sinks and source of information, so the sigma term is 0, and you can prove that because the system is isolated, the evolution is generated by a unique quantity, epsilon, which is the energy function in the geometric picture, which is essentially the expectation value of the Hamiltonian for an arbitrary state, that depends on the specific state where you are. And this is how the evolution of, excuse me, of the probability density looks like. You have a notion of Poisson brackets. And so basically dq over dt is given by the Poisson bracket between epsilon and q of t. And because the flow is Hamiltonian, you can write it explicitly. Let me use the pen. And this is how it looks like, where v epsilon, and here I've written it for an arbitrary high dimensional quantum systems, where instead of having p and phi, you have vectors pn and phi n, which are probabilities and coordinates in a given basis. And in particular, if you use, for example, for a qubit, if you use the basis that diagonalizes the Hamiltonian, you can recover the standard, the standard evolution. So again, this was just to present a general result for isolated quantum system. You can, for people who are interested in, sorry, give me 1 second. There's a little bit of noise. All right. So for the people who are kind of more into the mathematical part of this, essentially this means that isolated systems have you can prove a Liouville's theorem for isolated systems, and as you'll see now, you can also prove it for open quantum systems with this language. So what is the strategy to use this theory for open quantum systems? First part is to do kind of a kinetic theory, in the sense to set up kinetic equations to do the foundations, and then do coarse graining and study the flows of information at a more coarse grain level. Now, of course, the kinetic theory is absolutely necessary for the foundation, and the way you derive the kinetic equations for the probability density is the following. You know that there is an overall Hamiltonian, and that you split in, it's the standard setup of open quantum systems. So you have Hamiltonian of the system, Hamiltonian of the environment, and Hamiltonian for the interacting part. Now, when you do that, and then you use the theorem, and we've said that already. Essentially at finite dimensional for finite environments, the geometric quantum state, it's a sum of Dirac deltas. So essentially you have two set of variables, the x alpha and the y alpha, and this is just for mathematical convenience, for compactness of presenting the evolution. You can define a unique vector. It's a non-normalized vector in the Hilbert space that is square root of x alpha y alpha. And you can check that basically the global Schrödinger's equation maps into this equation. This is a Schrödinger equation. This is a set of coupled Schrödinger's equation, where H alpha is essentially a modification of the Hamiltonian of the system, and V alpha is an operator. It's a set of operators that act on the system, that basically is built out of HE and in particular H, the interaction part. Now, from that, you can prove the two following things. First, the probability vector x alpha evolves in this way, and it's more convenient to write the evolution for the square root. This is because this is just a mathematical convenience, because you're mapping, essentially the defining characteristic of probabilities is that they are larger than 0 and they all sum to 1. So sum over alpha x alpha equal to 1 is equivalent to sum over alpha square root of x alpha to the square equal to 1, which is the equation of a sphere. And so there, basically, it's easier to do the evolution with these coordinates just because we have a bunch of properties that we can impose or we can verify in this case on the matrix Q, and you can check that they're all verified. So Q is essentially a matrix that rotates that vector appropriately and does depend only on the interacting part of the Hamiltonian. And you can prove that basically each of the vectors y alpha, they evolve with a time-dependent Hamiltonian that is peculiar for that value of alpha. And the actual form of M alpha here, it's really not relevant. So I just omitted it. It's a function of mostly the interacting part. But geometrically, what this proves, and you can prove it directly, is that the evolution of each of the point, it's provided by a separate Hamiltonian. And in this case, the Hamiltonian is time-dependent. So you have a description in which you have the points that move around the sphere with a certain time-dependent Hamiltonian, or there's an equivalent description in which you have basically a bunch of points that run around the sphere, but with a Hamiltonian that's not a one-body Hamiltonian like in this case, so one for each point, but it's a two-body Hamiltonian. So each point has a co-evolves with all the other points. So these are the kinetic equations. This is the first step. And then, of course, what you do, you go into the phase space of your quantum system. You fix the size of a cell, and you do coarse graining. How to do this coarse graining, it's a little bit non-trivial because of the non-trivial properties of the geometry. Namely, this is not a flat space. So there is a notion of metric, there is a notion of symplectic to form. So one has to be a little bit careful with the geometry, but you can absolutely do that. And in this case, I've shown you, this is for qubit, and this is the P part, and this is the phi part. And so you can put a grid on it and do basically coarse graining on this. And you take the three principal actors of the continuity equation, so the geometric quantum state Q, the flux of information J, and the sink and source term, and you coarse grain, you integrate them on the elemental cell, and you get discrete quantities mu AB, FAB, and sigma AB of T. And in particular, FAB has the nice interpretation of being the flux of the probability flow across the boundary of that cell. So it's in this picture, it's essentially measuring how many particles go across each boundary and how fast they do it. Right, so you get a coarse grained continuity equation with FAB and with the discretized quantity. And so you can come up with, for example, simple models like rate equations in which you imagine that, there is a bunch of points. Sorry, this is my cell AB. There's a bunch of points here. And in first approximation, I'm just coming up with realistic models to kind of showcase how you can use the theory. Let's imagine for a second that sigma z is equal to 0, so that there is no sink and source term. Then obviously what you have is that basically the only way the probability can change inside the red square AB is for the particles to basically move either up, down, or left and right, because there are only 2 dimensions. And you can imagine situations in which you have rate equations. So essentially there is a constant flow. And so you have that the amount of particles that move from the cell AB to the neighboring cell in the P direction is given, it's a fixed fraction as a function of time. And so you have gamma P times the amount of probability inside the 2 neighboring cell, because you have these 2 kind of phenomena, right? And the going inside is this part, gamma P and gamma phi, because this is true in the p direction, sorry, in the p direction and in the phi direction. And then you have a loss term, because of course, for the same reason, particles are going outside the cell AB. This follows from some kind of assumption like there is no special cell, so they all have very similar behavior. And the conservation of probability gives you a relation between the loss term, and the gain parts, the gain coefficients. The continuum, you can, that rate equation, you can perform the continuum limit, and it actually gives you, this is why I've chosen it, because it's a simple model and a lot of people know of this. This gives you a fixed law of diffusion for quantum information flows, in the sense that you can check that the continuum limit of that rate equation gives you a flow that is basically the gradient of the probability distribution. And as a result of that, the continuity equation turns into a diffusion equation over the phase space. This is another example in which the modeling was not done. Why is it not? The modeling was not done kind of analytically, but it was done to perform numerical analysis on it. And this is the same case that I've shown you in the, well, no, it's not that same case. It's a ferromagnetic Ising model. So it's very similar to the previous case I've shown you in the sphere, but the interaction is actually different. And on the left, you can see the P5 probability space. And don't bother about the right. This is just basically a maximum entropy. I was checking if the maximum entropy assumption was kind of realistic for that system. And you can see that in the ferromagnetic case, so here the visual representation is slightly different, because the probability mass is represented by the size of the circle that you see. So you can check that there is basically, there's a lot of probability mass in this low region. And so if you do the time average of this probability distribution, you get something that is localized. So you have information that basically is retained in a certain region of the quantum state space. And so this is basically numerical analysis in which you take, you take that big square, you put a grid on it, and for each element of the grid, you look at a function of time, how probability gets in and gets out. And maybe you do a time average because you're interested in thermalization problems or equilibration problem, long-term dynamics problem. All right. So we're almost near the end. Let me check. Yes. So the main point here is the following. It seems that at the most fundamental level, the way information flows in the state space of an open quantum system basically follows the laws of Hamiltonian mechanics. It's a particular Hamiltonian mechanics in the sense that it has a Hamiltonian and all of that, but there is some additional geometric picture that encodes the quantumness of this system. Now, the advantage of this, hopefully, would be that moving forward, we can try and use tools from the theory of dynamical systems and non-equilibrium classical statistical mechanics to study open quantum systems, both analytically and numerically. And hopefully, one of the main reason is that, classical statistical mechanics has been developed for a long time, and systems, the study of these systems is, I think, more advanced than what we have in quantum theory, just because you can prove more theorems and more people have worked on it. And so my hope is that we can basically, because of this geometric picture, we can basically take all that setup and just import it in here, trying to extract rigorous results, for example, about thermalization time or about how information flows in an open quantum system in an actual quantum hardware. There is a lot of talk about quantum hardware and quantum computers. So being able to kind of understand how a quantum hardware moves information on the state space of a quantum system would definitely help us understand the power of quantum algorithms, for example. Now, before I actually close, I want to mention something I was telling Francesco at the beginning, and it's that, so this is a more, I propose here a kinetic theory of information transport, but as you have seen, a lot of the interest and the tools are, part of the interest is in developing the tools themselves, because they might lead to different results and new, and they might be able to help us in solving problems that we couldn't solve before. So I just want to mention very briefly a collection of other results that one can derive using this geometric picture. So I've shown that there is a notion of thermodynamics that can be slightly different from standard quantum statistical mechanics, because the ensemble there is not just a direct sum of eigenvectors of a Hamiltonian weighted with Boltzmann coefficient, but you could imagine the situation in which you have a continuous ensemble that has the e to the minus beta shape with a Hamiltonian on top of that, and you can check that it gives you results that are qualitatively compatible with standard Gibbs statistical mechanics, but they're also you can measure that, you can tell that there is a difference. We can talk about more about what this difference means. It's not important at this stage. You can also prove that there is a first law of thermodynamics. There is, these are full-fledged, it's a full thermodynamics. You have fluctuation theorems, you have a second law, and you have all the machinery. But it's slightly different than the standard quantum thermodynamics. There are new tools of analysis that emerge, like, for example, this can be a continuous probability distribution, P of Z. So there is a notion of entropy, integral of P log P using the Fubini's 2D measure, that gives you something that is different. This is not the von Neumann entropy. It's actually lower bounded by the von Neumann entropy. And this is the general suggestion. Akira Sone and Sebastian Defner have used this functional successfully to connect it with classical and quantum thermodynamics, basically formulating the notion of ergotropy with this geometric formalism. There is a whole perspective in which basically you recognize that the state space of a quantum system is not discrete, it's continuous. So there is a plethora of tools that we can use, from analog information theory, the one that holds for continuous variables, that can be useful to tackle and to basically put more tools in our toolbox for the study of quantum systems. I was able to recently define a notion of quantum information dimensions, in the sense that you can have, like, what I've shown you is a bunch of Dirac deltas or smooth probability distributions. You can have situations in which these are really not nice probability distributions, in the sense they have support on a fractal. And if you're wondering if this is real or not real, yes, this is actually the geometric quantum state that you get from the ground state of a Heisenberg Hamiltonian with a defect. So the presence of the defect induces this kind of fractal structure in the geometric quantum state, and you can check that it has a non-integer, that's a set that has a non-integer dimension that kind of reminds you of the Cantor set. So the suggestion here that this should lead to new ways of modeling non-equilibrium phenomena, and in particular using the dynamical systems perspective, using concept like basing of attractions or attractors and fractals. And of course, in this case, I've shown you, the evolution with for a globally pure thing, but the evolution of the geometric quantum state can actually be stochastic, right? And so one can easily define stochastic geometric quantum mechanics as a stochastic process on the sphere or on general high-dimensional quantum systems. And so with this, I want to conclude by just saying, I believe that geometric quantum mechanics can give us a new perspective on quantum phenomena and possibly their information flows. The point here is track ensembles using geometric quantum mechanics And the evolution should follow the laws of Hamiltonian mechanics. And so you can use the intuition not just from what we developed about open quantum systems, but also about what we know from classical non-equilibrium statistical mechanics. And that's it. Thank you.
Yeah, Fabio, thank you so much for this very refreshing look to closed and open quantum systems. Thank you very much. It was an excellent talk.
My pleasure.
We had already, thank you, some comments and questions during your talk. But please, to all the participants, you're welcome to unmute yourself and ask Fabio questions.
So I have a question.
Please.
So, okay, at some point in your talk, there was this equation that, I mean, when I looked at, I mean, the point is like, okay, you have I forgot, can you go backwards in your slides?
Sure.
It's actually, I think somewhere in the middle. Yeah, somewhere, yeah, yeah, here.
Here?
So, no, the one before. Yeah, so over here, this looks a little bit to me like, I mean, just correct me if I'm mistaken. Like what struck me is that this looks very much like what's it called? The Lindblad master equation that you get, of course, which you get like after you do all those various approximations. There are these secular approximations. Before that, there's, the other ones, like you first get the red field, then you do the Markov, then blah, blah, blah. So now, is there a relate? I mean, so, okay, so one question is like, is this related to that? Am I right in, okay, rather the specific question is, am I right in picturing that in my mind when I have this without the, I mean, if I were to do that without the approximation, whatever I get some complicated expression, but am I right in picturing that in my mind over here?
So the true and full answer is that truly, I'm not entirely sure, because this is ongoing work. And so this is work that I have not yet published. So I'm very much interested in connecting these with the tools of open quantum system theory. Now, with that premise, I can tell you what I think and what I believe to be true. So this is like a rate equation in which terms don't depend on time. And the number of states that you have here, it's labeled by alpha. Oh, sorry. It's labeled by alpha, so it scales with the dimension of the environment. So what does that mean? This is not Lindblad equation. Lindblad equation is for it's for the density matrix. So what you would have to do to get Lindblad equation, you would have to here you have d over dt of a ket y alpha.
Right.
You put the bra y alpha, and then you sum overall alpha, and then you check that all those approximations are true, and you should get defined like this. You should get a Lindblad equation. The advantage of this is in practical terms is that there are gonna be a lot of states which don't matter, or rather, statistically, like if we think about about all those points on the sphere, intuitively, the number of points grows exponentially with the environment size. So very quickly, you're not going to be able to talk about points moving on the sphere, but you'll need to talk about a continuous probability distribution that is changing shape on the sphere. Right. So the idea would be to develop approximation schemes that are built on this. And the goal should be that ideally, because they're built from the microscopic model, they should be able to go beyond the Lindblad approximation, but without without having to go through all the pain of solving the Nakajima-Zwanzig equation, which is, as we know, it's very hard. So the hope, it's not a statement because I don't know yet, but the hope is that this could help. It could be some kind of in between, so that you can try and get the best from both worlds. you should get the best from a rate equation, so that, you know, coefficients don't depend on time and you have a kind of a simplified structure. But probably a lot of these y alpha don't matter, they don't change in time, or, you know, the x alpha, they become constant after a certain time scale. I verified that this is true in a lot of cases. And so you should have a lot of simplification. So this should lead you to some effective equation for each of the state, for each of the y alpha and the x alpha, from where you derive the equation for the density matrix. So the point here that I want to stress is that something that I've not seen, or I've seen partially, is when we talk about Lindblad and this kind of thing, the goal is to model the evolution of the density matrix.
Right.
What I'm trying to do is I'm trying to put a step in between so that hopefully we come up with models that are more accurate. And the step in between is model the ensemble, the environmental induced ensemble, and then get an equation for the density matrix.
Oh, right.
Okay. But again, so this is all work in progress, right? This is the idea that I have in mind. I'm not entirely sure how practically successful it's going to be. I can tell you that I'm going to try, that's for sure.
Okay, so can I just ask another one? Like, so this is about like trying to get my understanding. So the idea of doing the coarse graining that you do a few slides later, right, the idea is precisely because like you want to sort of study a continuum, right? That is where.
Yes. So the idea there, it falls with what we said so far. Because of the number of points grows with the dimension of the Hilbert space of the environment.
Right.
Ideally, the continuum limit, it's something that should work better for large environments, but large here, we have to remember that it grows exponential with the size of the environment. So an environment of 100 qubits would be more than enough to have a continuous, like even visually, you're not going to be able to distinguish. So the hope is that maybe we can use some of these techniques for small systems in small and highly structured environments, but maybe not so small, like, you know, 5 qubits environment that you can simulate with you know, you can just do hexadiagonalization.
Right.
So yeah, that's the idea so all these particles moves in this space, right?
Right.
And so one would think that in some kind of hydrodynamic limit, you have like a continuous density that kind of stays constant, but it fluctuates a little bit, and maybe you have some collective behavior like I've shown you here, right? Why is it not? Oh yeah. Right here in this region, you have probability that keeps hovering and hovering and hovering, right? And what else is happening doesn't really matter. You have, I mean, particles move all the way. And so you have some kind of basic field that they grants you some kind of continuity. And then on top of this, you have some emergent behavior. So the idea would be that these techniques should be able to help us in recognizing those kinds of emergent behavior. But yeah, that's.
Thanks, that helps quite a bit. Thanks.
For sure, my pleasure. Thank you for the question.
Yeah, maybe we have time for one more question. Is there is some further urgent need for explanations? Anyone? I see Darius unmuted himself. Please, Darius, go ahead.
Maybe just a small comment.
Please.
Thank you, Fabio, for the very nice.
Thank you for attending.
Interestingly, this geometric formulation of quantum mechanics has also a nice connection to general relativity, right?
Yeah.
Because, well, you mentioned these nice papers of Strokey and then Brody and Hangston, but there were also very, very nice paper by Ashtekar and one.
Oh yeah. Ashtekar and
Schilling.
And Schilling. Thank you.
Yeah.
Yes.
And what they observe, well, Ashtekar, is a very prominent guy, especially this loop quantum gravity.
I know. I've studied loop quantum gravity. Yeah. I've worked in.
Okay. And what they observe is that there is one-to-one correspondence between quantum observables and Killing vector fields, right?
Basically, yes.
Yeah. So it might be also that your kinetic equation has also some, closer connection to something which is, very much, related to general relativity.
Right. Yeah. No, that's for sure true. Yes, because there's this weird thing, right, that we don't recognize in classical mechanics, that observables have this dual nature, right? That they are things that we measure, but they're also the generators of transformations, of physical transformations. Yeah.
Yes.
No, you're right. Yes.
Okay.
So they're to some extent. So the what I have not mentioned is that the Schrödinger flow is a killing flow.
Absolutely.
So the Hamiltonian vector field that derives from a global unitary Schrödinger equation is a killing field. So that means that in here, all of these are killing fields. All the M alphas are killing fields.
And so, I see. So that's nice.
And so what does that mean practically? I think that if I'm trying to take your suggestion and tell me if I'm wrong, but the idea would be that if these, of course, correspond to some observables, right? So it stands to reason that in certain physical situations, there are certain observables that don't matter, right? You just throw them away, you don't make any mistake. While there's other ones, they're very, very important. They actually drive the evolution. So recognizing which one are important. No, I agree. You're absolutely right. It's just, there are a lot of, there's just a lot to do, right? Because the formalism of geometric quantum mechanics is not as advanced as, standard quantum formalism. Even just the definition of entropy, that notion of the integral of the geometric entropy, it's not truly well studied. There are a couple of papers on it, but we don't really have a good notion of mutual information. All of those things that give us a lot of practical tools. We just don't have them. So it takes. So all that idea, I think it's right on point, but I don't have the tool to actually go and do it. So I need to first develop the tools and then actually solve some real life and hard problem. But yeah, I agree. Those observables, there are going to be certain ones that are much more important than other ones. Thank you.
Okay, thank you.
Yeah, thank you very much, Darius, for that interesting question, because I would have liked to go down that road as well. So Fabio, thank you so much. I'm just worried now because in our part of the world, it's time to go for dinner. and for you, probably it's time to have breakfast. Yeah. So Fabio, thank you so much. It was really nice to engage with you and to listen to the very interesting work that you're doing. And I hope that we will stay in touch. And since we know all agree that there are lots of open, interesting questions, I'm sure that some of the participants will start working tomorrow morning and contribute to develop this very interesting area of research. Yeah.
I would love to hear from anyone, and please, if you're interested, I would be very happy to talk about.
I told you already at the beginning when we had a little chat that we are definitely very interested in establishing some side of collaboration and we will definitely be in touch in the near future. Yeah. So Fabio, thank you very much.
Thank you.
Wish you a nice Friday and then our weekend starts just now.
Have a fun one.
You still have to do some work before your weekend starts. And to all the participants, thank you very much for joining us. And maybe next year we will try to organize some kind of webinar, global webinar like this with a little bit more regularity. And thank you very much for Darius and his team for joining us this evening, and of course to all the others as well. Yeah, thank you. Fabio, thank you very much. We will send you the link to your video tomorrow.
All right, thank you so much. And thank you for having me. It's been a pleasure.
Absolute pleasure. Good night, good day, and good night to the others.
Good night to you.
Bye. Bye-bye. Thank you very much. Thank you.